Okay, so you should see the presentation. Okay, good. So the last thing that I wanted to cover in um, in this lecture is using memoization, which we saw in the last class, for doing something a little bit more real, right? In particular, we are going to apply this on a well-known algorithm. Um, and the point that I want to sort of um, try to push is the fact that memoization is a general solution for dynamic programming. So the problem that you are going to look at is edit distance. It is also known as Levenstein distance. The idea is that in this problem you will be given two strings, and the question that we are asking is what is the cost of editing the first string in order to change it into the second string, right? And what do you mean by editing? The three operations that are allowed are insert, delete, and replace of characters, right? And we say that cost of each one is one each, right? So this is a very standard problem, right? Levenstein distance is a well-known problem. If you've done algorithms, you would have come across this problem previously, right? And the standard way of solving this is dynamic programming, right? So you would use dynamic programming to achieve an efficient solution. So the observation that we are going to sort of share in this lecture is that there is a nice algorithmic way of describing the problem, right? Which does not particularly care about efficiency, right? So, and what we'll see is that we will get efficiency for free through the use of memoization, right? So we will take the solution, we'll have to write some solution down, we'll write a solution. On the first look, it will be inefficient, and we will see that it is inefficient. And then what we will do is we will get efficiency for free through memoization. Okay. So just to remind you of what the Levenstein distance problem is. So here is edit distance between kitten and setting, right? So it takes two strings. I'm asking, okay, what is the cost of editing kitten to change it to setting? The solution is 3, right? And of course, we are looking for the minimal cost, right? So edit distance is the minimal cost for going from the string 1 to string 2. So you first change K to S, right? In kitten, you change K to S, replace the character to get sitten. You change the E to I, right? And finally insert a new character. You get sitten here. So insert a new character at the end, which will change it to sitting. So since there are 3 operations, the cost is 3. Okay, so that's the problem through an example. And of course, the idea is that the strings can be of different lengths, right? So it is of different lengths here. So how do we solve this problem? So here is the standard solution. Okay, so so there is a lot going on here. I will try to break it down, but it is not important that you understand the correctness of the algorithm here. What I want you to focus on is the implementation of the algorithm, right? The structure of the algorithm, right? So let's break it down bit by bit. So edit distance is a function, right? It's a recursive function. There is an optional argument log. We'll ignore that for the moment. That's just turning off, on and off printing. It takes 2 strings, right? It takes a S and a T. And the question is, what is the cost for going from S to T using insert, replace, or delete? Two string operations here. So the thing that we match with here is the length of strings of S and T. Okay, so so the first thing that we do is we pattern match on these 2 patterns. So the pattern says that if either of these strings are actually empty, the string length is 0, then the edit distance is the length of the other string, right? So because if one of the strings is 0, then you can get from one to the other by deleting the characters one by one or inserting the characters one by one, right? That's easy. So if the strings are of non-zero lengths, both of the strings are of non-zero lengths, what we are going to do is to get the substrings of S and T, S prime and T prime. The substring is constructed such that it just does not have the last character. Right? We just drop the last character. Right? So we are essentially breaking down the problem into smaller problem. And the way we actually compute the edit distance is there are going to be three possibilities, right? And we are going to get the minimum of these three possibilities because edit distance is the minimum distance to go from one to the other, right? What are the three possibilities? The three possibilities are compute the edit distance to go from S prime to T. S prime is S without the last character, right? Compute the edit distance for going from S prime to T. And if the cost of that is some C, then the cost of going from S to T is that C plus 1. What is this additional one? The additional one is there in order to delete the character of S, right? In order to go from S to S prime, you need to delete it. So that is why we have plus 1 here. And similarly, we also explore the other possibility, which is compute the cost of going from S to T prime, right? Where you, and if the cost is 3, then the cost of going from S to T is that plus 1. And yeah, okay, sorry. So the cost of that is inserting the last character to T prime, right? So, okay, so because T prime is obtained by deleting that character. So if you can go from S to T prime, then you need to insert the last character to go to T, and that is the cost for 1. And the third case is compute the edit distance between S prime and T prime, right? And if the last characters of S and T are the same, then you don't need to do anything, right? So no change, no cost for if the last characters are both the same. In case the last characters are different, then you add cost 1 because you need to change the last character of S to T, and the cost for that is 1, right? So, okay, so this is the algorithm. So I'm not going to explain how this algorithm works, but what I want you to focus on is that there are 3 recursive calls, right? 1, 2, and 3, right? So naively, if you just run this algorithm, what will happen is you will have several invocations of the same function with the same argument, right? We will see how this appears. What we are going to aim to do is to make sure that these repeated invocations are all memoized in the sense that if you've seen those particular arguments earlier, we will say, okay, we'll just retrieve the result that we've previously done, and we will see how that helps. The other thing that we do here is if the log is true, then we print S and T. This is just for debugging, right? So it prints S equals that string S, T equals that string T. Okay, so with that, I will run this program just to show how this works. So I'm using the time it function from earlier. So I'm going to compute the edit distance between OCaml and OCaml. So the difference is we are replacing, these are capital letters, these are small, right? So the edit distance is 2, right? And it took 3 milliseconds to compute this, right? I've turned off log. Let me turn on the log. There is a lot of recursive calls, right? I mean, there is a lot. It's still going on. The thing that I want you to notice is there is a repeated invocation. So there is S, O, there is O and empty string. There is O and empty string here. I think there will be some O and empty string again, right? There are multiple invocations of O and empty string over and over again. So this is taking a long time, right? That is why this function is now taking a long time. Actually, this function completed, let's put it back to false. This function completed in what, 2 milliseconds with this string, right? 2 milliseconds doesn't sound bad, but this is the cost is really bad. The running time is really bad for longer strings. In particular, if I just change the string such that I add the same suffix 4.08, 4.08, right? And the only difference is OC here, the same OC here. Now look at the running time. It's taking a long time because the running time just explodes because of all of the recursive calls. It's still going on. Let's wait for a second. It's still going on. Okay. That took 14 seconds, right? So, and the edit distance is still 2. So this obviously is not a great algorithm, right? You want to apply this algorithm on very long strings, right? So I'm going to take two genetic sequences and I'm going to find how similar those genetic sequences are, right? If you sort of have a, so these are going to contain those 4 characters, right? And then you're going to see these very long strings, and you're going to ask what is the edit distance between the two, so that you find common similar looking genes using this algorithm. Of course, this algorithm as it is written down is not going to work because it is so inefficient. How can we make this efficient? Let's use memoization, right? The only difference between the previous implementation and the implementation that is described here is to make it suitable for memoization, right? So all I've done is I've added an extra argument for the recursive call f, and I replaced the recursive invocations with f's here, right? So this is a non-recursive function. I shouldn't need have a recursive annotation here, but otherwise the function is the same. Okay, so now let's memoize it using the recursive memo function that we've seen in the last class. So I'm memoizing that implementation now. And if I run this program now, it runs in 0.62 milliseconds, right? So earlier it took 14 milliseconds. And the other thing that I want to show here is if you actually turn on the log, you will see that we still do a lot of comparisons, but take my word for it, none of there are no 2 similar comparisons, right? So we won't ever see the same comparison again because we are actually memoizing everything. So once you actually have the previous result, we are reusing it. So the point to take away here, right? So what we've done is we have a dynamic programming implementation which is almost comes for free from the direct inefficient implementation, right? You have an algorithmic description of a well-known algorithm, and if you actually want to make it run fast, you'll have to do something. And because of everything being functional here, right? Everything is purely functional. We are not manipulating any state, except for the implicit state manipulation that occurs within the memoization. We are not doing anything else, but still we get very good performance, right? So the high-level point to take away, right? So is that imagine if you were to write this in C, the same algorithm in C, and get a similar performance. If you had to do it by hand without having this memoric functions and so on, of course you can make it go faster than what I've done here, right? So I've done a very naive one with caches that keep on building and so on. You can of course make it maybe go 10 times faster. But the question you need to ask is, C gives a lot of performance all the time, right? But what do you lose for that performance? You get you lose type safety, right? It's weakly typed. It is also the case that the cost of actually arriving at a correct solution is much more difficult, right? So of course you want to think about implementing critical paths, performance sensitive paths in C, but most of the code that is there, even in like things like operating systems, are not performance sensitive. So it is not always necessary that you want C, right, all the time. So in summary, the idea is that laziness and memoization make sense only in a pure setting, right? So because if your program has side effects and if you depend on those side effects to be required for correctness, of course we have side effects in this memoization example that we saw earlier. We just printed the log, and of course we only printed the log once because the effect was memoized. But if your function specification requires side effects, say sending messages on the network, or just manipulating data structures in a side affecting way, you cannot apply memoization or laziness, right? So The thing to note is OCaml doesn't prevent you from performing side effects in your program. You can throw references anywhere, arrays anywhere. We are not going to get any guarantees from the compiler itself that it doesn't do any side effects. In that way, it is the same as C, C++, Java, Python, Rust, Swift, JavaScript, all of these languages, right? You can have side effects anywhere, but partitioning your program into parts that are using side effects and ones which don't is useful, right? For reasoning, but also for using things like memoization and laziness. Of course, there are languages like Haskell which track side effects in the type system. So when you write Haskell programs, you can use mutable features. All of them are sort of compartmentalized in one way, and they are kept separate from the pure parts of the code. Right? And the high-level takeaway is this, right? Purity lets you take advantage of nicer reasoning, but also these sort of features. Make your code pure if your performance is not critical, right? So I mean, I say that with a piece of salt. It doesn't mean that pure code needs to be inefficient, but don't think about using mutable features in order to get maximum performance before you even have a solution for whether something is performance critical or not. Right? That's the high level idea. And if you keep something to be pure, you get other benefits. Right? So that's the summary. So that is the lecture on streams, laziness, and memoization. So any questions on the material that we've covered in this lecture so far? While I set up the next lecture. I'll give a minute. You can think about if you have any questions.
Sir,
Yep.
sir, I had a doubt regarding let's suppose we have a doubly linked list,
Uh-huh.
and in that, if I have any node, so
Mm.
camel is like a functional language, so there'll be a single data structure in the memory to which we are pointing right now. So
Yeah.
so when we are accessing, let's suppose the previous or the next of this node,
Yeah.
so like how do we know that this is exactly the previous or next of the this current node, or are we creating a copy of this thing?
So so you have a node, right, that has previous and next,
Yes, sir.
right? And what do you want to know?
So let's suppose let's take a list for example. Let's say
Yeah.
I have a list of 1, 2, 3. Let's suppose,
Okay.
and if I'm at 1, and if I use the pattern matching to deconstruct it into 1 is the head and 2 and 3
Yeah.
is another list.
Yeah.
So when I'm trying to access this 2 and 3 in
Yeah.
the actual memory, is it kind of an alias for the actual 2 and 3, or do I have another data structure which is having the same value?
Typically, it is alias, right? So, but it doesn't matter. Why does it matter? Because it's you cannot mutate that list, right?
Yes, sir. But
So,
in the
yeah,
case of linked lists, if I have mutable things, so in
yeah,
that it matters, right? If I'm
yeah, yeah,
modifying the next
yeah,
thing or
yeah.
not.
There, it is not a new list, so it doesn't copy it. Um, so if you have a list and then you say, get me the tail of the list, right? You write a function which returns the head of the list and the tail of the list. And the thing that you get back is the alias to the head and tail. So you don't create new lists. You'll only create new lists when you actually use constructors to construct a new list.
Sir, so
That's so when you
so if
yeah,
I have any
go ahead.
function and I'm passing all the arguments will be passed by reference, right?
Yeah, reference. Yeah, everything is
Okay,
reference.
sir. Yeah, got it. Thank
Yeah. So yeah, good question. So everything is by reference. Um, you don't need to worry about the differences. Yeah, everything is by reference. Okay. So there's a question on chat. Why isn't the type of lazy stream not recursive? As in, why don't we use the rect keyword? Let me get that up. So lazy values. So why is this not recursive, Nishit? You have a question. So these are this is recursive, right? This type stream is the same type as the one that I'm defining here. We don't use a rect keyword for the type, right? So types are always considered to be recursive. For values, yes. So let's look at a value. So these are just functions. So if I want to construct, so if I'm constructing a value, which is a lazy stream, right? Here I use the rect keyword because the thing that I'm defining here, the fibs lazy stream, is the one that I'm using here, right? So for values, you have to use the rect keyword. For types, they are always, So for types, they're always recursive. So whenever you say type, OCaml implicitly gives you the recursive type. Okay, so that was easy. So anything else? Any other questions? I've been posting a few tips and things to work with the assignments on the Slack channel. Right? If you've not been following it, do have a look. So these are posted in the general channel. This is based on the questions you're asking, right? So I'm sort of like getting principles out of it and sort of giving you tips to debug your program. Ask me more questions, you'll get more tips like this. It's hard to present all of this without some context. So do have a look at the Slack channel, ask me questions, and I'm sure you can also ask the TAs questions, right? So they will also be able to help. You can DM me if you are asking questions that are specific to your code in the assignment. It is better to send me a direct message or to the TAs, right? So I usually respond. Anyway, anything else? Okay, good. So in that case, let me move on to the next lecture. So in this lecture, we are going to look at what are known as monads, right? This is just a word. I'll explain what the idea is. Essentially, monads are a way of dealing with effects in a pure setting. So recall the conclusion that I mentioned in the last class, right? So OCaml is a language, it's a functional language. It gives you all the nice features of writing pure programs, but you can also mix and match things that have effects within them. So you can throw references in it, you can do whatever you want, right? So from a study of functional programming languages, right, when you sort of think about lambda calculus and so on, sometimes it is better to, we had nice properties for purely functional parts of the language, right? We had this nice Curry-Howard correspondence which said, oh, every type is like a proposition and every program is like a proof of that proposition. All of that sort of fails really badly if you add ML-like references which are not tracked into simply type lambda calculus. Monads are this nice way of like reasoning about effects in a pure setting, right? So there are many things, but they are just a nice way to reason about these side effects in a pure setting. So if you wanted just a pure subset of a language and you wanted to add effects to the language and still retain some notion of um, program reasoning, so Monad is a nice way to do it, right? So that is what we are going to look at. Actually, Monad is also a design pattern, so it sort of helps you organize your program in a nice way. We'll sort of motivate and look at why it is the case. So the term monad is really weird, right? So it is not, uh, it doesn't seem off this world. It is out of this world. Where does this come from? This comes from category theory. And category theory is the study of mathematical abstractions. So category theorists like to give names for everything, and they like to sort of give names which are completely made up and different from everything else, so that they can name things which are quite abstract, right? And monads is sort of the term monad is borrowed. The idea and the term monad is borrowed from category theory. Category theory itself is out of scope of this course. I'm not going to even touch upon that. But what we'll see is what is the programming aspect of monads. So there was a really nice paper back in '91 by this person called Phil Wadler. I'll share a link to that paper later. Who said there is this nice idea in category theory where mathematicians are looking at just mathematical abstractions, and he said, okay, if we take this idea and put it into an actual programming language, it makes some of the problems that we have easier, right? And that is how monads came to be in programming languages. And what we will do in this lecture is we'll just look at programming with monads, right? We are not going to look at, we're going to touch upon some principles, but not look at it in any detail. Okay. So, yeah, as I said, so this person borrowed, Phil Wadler borrowed the idea of monads from category theory, right? And then he was one of the key persons in the design of Haskell programming language. And Haskell is a purely functional programming language in the sense that in OCaml, we were able to throw side effects, right? Arrays and references wherever we wanted in the program, and it sort of worked out. In Haskell, we are not able to do that because the type system will say you cannot have any side effects in your purely functional code, right? So they are just completely encapsulated in some way. When a Haskell function is pure, when it says int arrow int, right? It has a contract that this particular function will not perform any side effects, right? This is very nice because just by looking at the type, you can know something about the function. And in particular, these pure functions behave like mathematical functions, what we saw in the earlier part of the course, right? And we broke all of this when we added side effects, but that's another story. But there was this question of how do you integrate side effects into a language like Haskell, which separates, which sort of encourages pure code all the time, right? And monads are a way to do it. You might ask why you would want monads in, say, OCaml, right? Where we can have side effects everywhere in the language. One thing monads allow you to do is they allow you to simulate and encapsulate side effects. In particular, there is a nice result which says that any effect that you want to simulate, by effects, you can mean, say, references, state, say, throwing exceptions, concurrency, parallelism, and so on. All of these could be simulated by monads in the sense that you can implement them as libraries. So if I wanted a concurrency library, if I wanted, say, high performance asynchronous programming library in OCaml, I will write the library using a monad just so that it simulates the presence of concurrency, which OCaml does not have, right? OCaml does not have native concurrency features, right? So the idea is that you can simulate advanced language features just by using a monad. And it might seem like monads are this intellectual curiosity that is only explored by these languages which are not widely used, Haskell and OCaml. But these sort of ideas are slowly coming into mainstream languages as well. Scala, for example, which is heavily used by Twitter, right? So they use monads everywhere. Um, and there are libraries which use monads. And of course, these ideas are also being borrowed into other languages. I've seen C++ libraries which use monadic programming pattern and so on. So the aim of this particular lecture is to give you an idea of what a monad is in a nice setting, right? So we are going to see simple examples and so on, so that you can see applications of it elsewhere. When you see it in, say, a JavaScript library, or when you see it in, say, a Rust library, right? When you actually end up using one of those languages, you can identify the programming patterns and hopefully understand the semantics of what they do, um, without delving into the implementation details, right? We are going to look at what they are more than how they are implemented. Right? So that's the idea of this lecture. And as I mentioned before, Monad is a design pattern, right? It's an idiom. It is not a primitive language feature. So just like you have design patterns in other languages, we can also have design patterns in OCaml. And Monad is just a design pattern. It's a way of organizing um, the program in such a way that it works for you, right? But it's not like a language feature that is embedded into the language. We are going to use all the language features that we've used previously in all of the previous lectures. We are going to borrow them. We are going to use it in this lecture. So, okay, so the first question, right, is what is a monad, right? What exactly is a monad? The answer is actually very simple but not useful. But I'll anyway give you the answer, and then we will look at examples to motivate why this is a useful answer. So a monad is any implementation that satisfies the following signature, right? So we have a module signature here, right? It's a module type monad, right? And it has three things, right? It has a type, it has two functions, return and bind. So any structure that satisfies the signature is um, is a monad, and in addition, it has to satisfy what are known as monad laws. We will see what those monad laws are. But if you can write a structure that satisfies the signature and the monad laws, then you have a monad. Right? So this answer is the very abstract one. It's not. It's not illustrative, right? It's not giving you any more information than when you started with when you asked this question. Let me try to refine it a little bit. So a monad, right, is meant to describe a computation. Computation could be anything. Let's leave it abstract. So the type of that computation is alpha t, right? There is some computation, something that computes, and the type of that computation is alpha t, where the alpha corresponds to the return value of the computation, right? When you run the computation, that's the result of the computation, right? So computation is this thing which I haven't defined, but when you evaluate that, run that computation, you get an alpha as a result. Right? And return is a function that takes some value alpha and then makes it into a computation, right? And the idea is that the computation will have some effects, but I also want to take values and make it into a computation such that it doesn't perform any interesting effects. But when this computation is run, you get the value back, this value back, right? That's return. And bind is a way of sequencing two computations, right? Ignore the signature for now. Bind is just binding two computations together to create a bigger computation. So take two computations. It's like a glorified semicolon in OCaml, right? In OCaml, you can take one printf, another printf, and then add a semicolon. You have an expression now which prints both of the things. Just like that, bind is like a glorified semicolon, which takes a computation alpha t, right? And it takes a function that takes the result of this computation, which itself returns a computation which is beta t. So there are two computation. One computation is the alpha t computation. Another one is the beta t computation. You're going to fuse them together, right? So at the end, you're going to get beta t. So you build a new computation, right, which is going to return you a beta t. That's the abstract description, right? So let's sort of keep that in the back of the mind. It's okay if all of this is not clear. The idea is monads describe computations, return values, lift a value to a computation, and bind takes two computations and sequences them together. That is all you need to know at this point. Okay, this all seems very abstract, right? And of course, many functional programming concepts are. Um, and in order to make it more clear, we will take a simple example that we understand, and then we will slowly motivate why we need monads, right? And that's what we will do in this lecture, hopefully. So what we are going to do is to write a very simple interpreter. We are going to write a very simple interpreter for arithmetic expressions. Okay. So here is the expression language that I have. So we define a type for expressions. The expression could be one of three things. It could be a value. It could be an integer value, right? It's a val of integer. So values are expressions. It could be the addition of two expressions, right? Plus expression 1 and expression 2. Or it could be expression 1 divided by expression 2. So there are only three kinds of expressions. And of course, this can be recursive, right? So these are expressions themselves. So a value, addition, or division, right? So we want to take the expressions that are defined using this, and we are going to write an interpreter that evaluates that to its final result. Okay. Okay. So with that, we'll define the interpreter. Um, the interpreter itself is very simple, right? So it's the interpreter that you will naturally define. The one thing that we are going to place a constraint on is to make our interpreter a total function. So what are total functions? Total functions always give you a value, right? When you, for every argument, a result is defined, right? So that's the input. That's the definition. And what does it mean to have totality for evaluation? You give it any expression, it will always evaluate to some value, right? That's the idea here. So what are we doing here? So evaluator, the interpreter, I call the function eval, is a recursive function. It pattern matches on the given expression, right? If the value is, if the expression is a value, then the result is just v, right? So I have a value, so the value is just, the result is just v. If the expression is e1 plus e2, first evaluate e1 to get a v1, then evaluate e2 to get a v2, and then you actually add them together to get the final result. And for division, it's similar, right? Evaluate e1 to get a v1, evaluate e2 to get a v2, and then v1 divided by v2 is the result of evaluating this expression. Right? These are recursive calls because they can be this e1 could itself be a more complex expression, which is like plus or division or so on. So the type of this evaluator is it takes an expression and then returns you an integer. That's the result of interpreting this expression, evaluating this expression. Okay, that should be fairly obvious. So let's take a step, right? So let's see some examples. So what I'm doing here is I've written down plus div val 4, val 2, val 7. The way to read this is it's better to look at it in infix form. It's basically encoding 4 divided by 2 plus 7, right? And the result is going to be 9. So if you run this, you're going to get 9. Oops. Let me clear the restart and clear output. And then let's run these things. So if you run this expression, you'll get a 9, right? So this is 2 plus 7 is 9. So the problem with this, right? So the thing that we really wanted is we want this function to be total, in the sense that whatever expression I give you, I need a integer as a result because that's the type that I've defined. But what happens when I have a division where the denominator of the division is a 0, right? And what happens in our evaluator, if I divide 1 by 0, I get an exception. I get a division by 0 exception in OCaml, which is precisely what I have here, right? And the point here is this is not a total function, right? If eval were a total function, whatever the input is this expression now. It should return me. It should return me what? It should return me an integer, but it is not returning me integer. It is not returning anything, right? It is throwing an exception. This is hence this function is not a total function, right? So I would say that because the specification says that it has to return an integer, and this function is not returning an integer, it is not a total function. So how can we avoid this, right? I want to make it a total function. So let me stop here. So any questions so far on this, on whatever I've said so far? Okay. So the point is to make sure that we don't throw an exception, right? And we've seen a trick to do this, right? Instead of throwing an exception, we can encode the result as a option type, right? So rewrite evaluator function such that it takes an expression and returns you an int option. The idea is that if the expression in fact had a division by 0, you'll get a none out. Otherwise, you will get some value, right? That's the idea. So return none for division by 0. Instead of throwing an exception, you will return division none, and that becomes total at that point, right? Whatever expression that you can construct, you will get one of the values of this type, right? It might be a none or some, but the specification here fully captures what the function is doing. So it becomes total at that point. Let's write the evaluator. It looks much bigger now. Why is this case? So we pattern match on E, right? If it's value, then we return some V, right? If it is a plus, then we first evaluate E1. When we call evaluate E1, it is possible that the result is none as well, right? Which means that E1 had a division by 0 exception, which is now returning none. So if E1 returns none, then this whole expression is also going to return none, right? You had a division by 0 exception, so return none. If E1 evaluates to some value V1, then go ahead and evaluate E2. And the same way, if E2 returns you none, which means evaluating E2 led to a division by 0 exception, then you return none because the whole thing is now just a division by 0 exception. And otherwise, if it returns V2, you have V1 and V2 now. So you make up V1 plus V2 and then wrap it in sum so that the type checker is satisfied, right? So that's the plus. And for division, you do the same thing for E1. If E1 evaluates to none, then you return none because evaluating E1 itself led to a division by 0 exception. If you evaluate E2, and if that returns none, return none. If it returns V2, here is where we have to make a check, right? So we have V1 and V2. If V2 is 0, V2 is the denominator, right? V2 is what we obtained by evaluating E2. So if V2 is 0, then we are going to get a division by 0 exception. Then we are going to say, okay, there is no result here. This corresponds to a division by 0 case. So here we return. If V2 is non-zero, then we return sum. Yeah, you can use try catch. Yeah, so so internally, yes, you can use a try catch, but the idea is that yeah, so you can use that as well. But the type will be the same, right? It'll be you'll have to convert that to this type. But yes, So as I mentioned earlier, right? So exceptions are also some sort of an effect, right? And we are going to try to write purely functional program, and then we are going to simulate the notion of exceptions and so on. So using an exception is sort of, I would say, let's not use exceptions here because we are going to try to define monads for that. But you're right, Sarthak. We can use you can use a try catch to handle this. Okay, so we've written this down, right? So this is nothing surprising here, and this works as expected, right? So if you do 4 divided by 2 plus 7, actually I haven't run this, so that's why you're not getting an optional value. So if you do this, then you get a sum 9, and if you evaluate 1 divided by 0, you get a none. So let me see how much time I have. I think I can explain this. So there's a lot of repeated code here, right? So there is a lot of repeated code here. In particular, if we evaluate an expression, if we evaluate it, then if it is none, then we return none. Otherwise, we go and evaluate E2. If it is none, return none. Then sum V2. The interesting thing happens here, right? All of this is sort of the same between plus and between division, right? So we have a lot of common code here that we've repeated, right? The only interesting bit is for addition, this happens. For division, this happens, right? So let's try to sort of extract the common parts into some function, right? That is what we will do. And the way we'll do it is through two helper functions, right? I use the name return and bind because I'm defining a monad, but you can, for the sake of this example, you could have called it anything that you wanted, right? So what I'm going to do is to say I'm going to define a function called return that is just going to wrap that given value in a sum constructor and return it. So it is just a return is just an alias for sum here. And I define this function bind, right? And it takes a it takes an m, which is an optional value, which is the result of evaluating an expression, right? It is an expression which, when evaluated, gives you an optional value. If the optional value is none, then I return none. And what is f here? F is the thing that you do on the value if it is not none, right? So I take a function f, which is what you do if this thing actually, the m actually evaluates to some value, right? If it evaluates to a v, I'm going to apply f to v, right? So to go back here, what I'm abstracting here, the match m with none to none and some v is the thing that you see here in this implementation. It's match e1 with some v1, right? And f is the thing that you do here, right? F is the thing that you do here. With v1, what are you going to do? Right? I'm sort of making that into the higher order function. And for the second one, this is the thing that I've abstracted, and this is going to be captured by f. Right? So that is what I have here. Right? So so f is the function that you apply when the value actually evaluates to some value. It doesn't throw a division by 0 exception. Right? Okay. So now, given that we have these two functions, right? Let us rewrite the interpreter to use this, right? So I've rewritten it down here. So as I mentioned before, what we have to do for eval e1. So what we have done is we evaluated e1. It could return either none or some. If it returns none, it is none. If it returns some value b, then we do something else, right? And that is precisely what we have here. For bind, we say evaluate e1, right? Go ahead and evaluate e1, and we apply bind to it. The semantics is that if evaluating e1 returns none, then we are going to return none. If evaluating e1 returns some value v, then we are going to take this function, This whole thing is the function, right? That's the rest of the computation in the case of plus. We're going to take this whole thing and we are going to say, okay, this V that you get as a result of evaluating E1, just bind that to V1 and just do whatever the body says. What do we do in the body? We say, okay, now evaluate E2, right? And if E2 is going to evaluate to none, then we are going to return none. That is what I achieve with bind. By applying bind to this um, term, if it evaluates to none, then we get none back. If it evaluates to some value V, then that value gets bound to V2, right? So I get V1 and V2. So this function goes all the way from here to here, right? I get V2 here. So you get here only if both of the E1 and E2 evaluate to some value, right? If none of E1 and E2 actually have a division by zero exception, then you come here, you get both the values, and the last thing you do is return V1 plus V2. Again, return is forget the C semantics for return. We are not doing C now. Just put that away for the moment. Return here just says it wraps the thing in some constructor, right? So this whole thing now returns some V1 plus V2, which is what we wanted. It's just returned in this weird syntax because I want to make a point. But that is what is happening here. So just the same thing that we had written earlier, return using these two functions now, right? And the same for division. So evaluate E1. If that evaluates to none, then this whole thing, this bind, right, says that if it evaluates to none, this whole expression is none, because the function itself goes from here all the way to the end, goes from here to the end, right? If it evaluates to some value, then the value gets bound to V1. And what do you do with that value? Go and evaluate E2. If that evaluates to a value, then bind that to V2. Now we have V1 and V2. Now go and do the check because we know V2 is the denominator. If V2 is 0, then the whole thing is none. Otherwise, return V1 divided by V2. So all I've done is I've just rewritten the previous example here. This whole thing, this big thing, down to the smaller expression, right? Yeah, again, so this is one way of writing it. I've still not made the point, but let me stop here because I've already taken a lot of time. You must have questions here, so I will wait a few minutes so that you can ask questions on this. The thing to note here is the one thing to note here is this function, right? This bind, the bind takes an m and an f. The m here is eval e1, right? That's just the term that we have here. This f is this function that goes all the way to the end here, right? So that's the weird bit. So it's like saying, what should I do if this eval goes to a value? Is do all of this computation, right? We sort of encapsulate that in a function. And similarly, the function f argument for the second bind goes all the way from here to here, right? Yeah. Otherwise, I think the syntax might be a bit odd, but if you sort of expand bind in place, if you replace every bind here, right, with the definition here, you will get the previous implementation. Yeah. Yeah, bind and you're right, Venkat. So bind and here are very specific, right? We are defining one sort of computation. This is a computation which will encode an optional value. So bind and return, you're very right in saying that These binds are very specific to the computation that we are defining here. So it's not defined the same way everywhere. So we'll see different notions of return and bind. Each one will be a different monad. Okay, so yeah, if you have other questions, ping me on Slack. I'll be around and I can answer the questions. Okay, so I'll stop here. Thank you very much. I'll see you next week.